Well, welcome to Chapter 7, the question number 3 from the book Fundamentals of Particle Technology. This is a fluidization question, and it's all about bed expansion. That's when the porous medium initially at rest is then fluidized, and then it opens out to form a certain voidage or porosity that's higher than the original at rest value. And then if you increase the flow rate even more of the fluid that's fluidizing, then the bed expands further in a nice uniform way. So that's really a particulate type of fluidization that we're talking about. And here is question 3 that's in front of us. There's quite a lot of words to it. I'll probably have to scroll backwards and forwards to sort of tick off as we go through it. Let's start though with the basic question, which is similar to how we started in the last problem, which is to work out the voidage of the bed. Okay, so here we have our porous media again. The fluidizing gas in this particular case is coming up here. It's flowing past the particles and fluidizing them. And we're told that this particular bed has a diameter, an internal diameter of 30 centimeters. So in this case we've got 30 squared just there. We still need d squared over 4, that's the cross-sectional area of a circle. And then we still need to multiply by 20. So that is our calculation of the volume of the bed. I'll use my trusty calculator. I think it's one I should be able to do in my head, but for the sake of completeness, let's try 30 times 30 times 20 divided by 4 times by 3.14. So that gives 14,130, which I might be able to just put into here. So that's 14,130 centimeters cubed, or milliliters, they're the same thing. I'll use milliliters simply because it's easy to write. And then we have the density, which is mass over volume, kilograms per meter cubed. So you can get that equation simply from the units of density. And the mass of the bed in this instance is 1,800 grams. 1,800 grams. Okay. I don't want to know what the density is, I want to know the volume, what the volume is. So that's mass over density of 1.3. So the volume of solids is, going back to the calculator, 1,800 divided by 1.3, because we're in CGS units, not SI units. So that is, can't really see it very easily, the light's not very good. I think that is 1385, near enough. 1385. 1385 mils. And therefore the concentration is going to be 1385 over 14,130. So let's just divide that by 14130. Gives us 0.098. 0.098. And that's a volume to volume solids per volume of the bed. And our voidage, which is what we're really being asked for, is equal to 1 minus the solid's concentration, so that is equal to 0.902. Again, dimensionless, volume of voids divided volume of bed. So that's the first question, 0.902. Yep, it's one of the answers, that's good. So the answer is in fact this one here. Okay, right. Now the next bit is all to do with calculating the particle Reynolds number. Okay, the really important bit here is the particle Reynolds number. It's not the modified Reynolds number that we're calculating. And we're told that the settling velocity is this value obtained from the Hayward tables, and we've been asked to check out check that that's correct. So let's do that, because we can check the values on the Hayward tables online. So if I select, here we go. The Hayward tables here have been programmed in to the website Particles.org UK settling index, and if we enter our values rather than the default values, the particle size is 200 microns. The particle density is 1300 in SI units. The fluid density is 1.29. It's a gas, 1.29. Just check, yeah, that's right. And the fluid viscosity is 0.00002. Okay, so if we calculate, press the calculate button, that tells us what the settling velocity will be according to the Hayward tables as well as Stokes, because the settling velocity here is near enough 0.781, which is slightly less than what we said in the question. This is more accurate than the using the tables. The difference there is so small. It's 2 in 780, so it's well less than 1%. So the settling velocity is 0.781 or 0.783 meters per second. Interestingly, the Stokes's predicted velocity is actually more or less twice that. Reason being that Stokes doesn't take into account any of the form drag, any of the turbulences around the particle. So it's a massive difference. In fact, the online system also tells us what the particle Reynolds number is, which is the next question. So we know to expect something like 10.1. Anyway, so we validated the value to use in the question, which was 0.783, as indicated here. So we've done that validation, and we know the answer is 10.1. However, I feel the need to just check that out. If I was doing this rather than just relying on the website, there we have the voidage put in. Here we have the density of the solid, density of the fluid, and the density difference. Here we have the particle diameter converted to SI units. Here is the viscosity, and here is the terminal settling velocity. To two significant figures, it's 0.78 either way, whether it's a 1 or a 3 afterwards. So the question is, how do we calculate the particle Reynolds number? There's a placeholder here. It's not a value of 1. So all Reynolds numbers are ratio of inertial to viscous forces. The particle Reynolds number is particle diameter. That's our characteristic linear dimension. So let's put the real value of particle Reynolds number in here. So that's our diameter. Now we need to multiply by the terminal velocity. Then we need to multiply by the density of the fluid, du rho. Okay. Then we need to divide by the viscosity of the fluid, du rho over mu. So that should give us particle Reynolds number, and it's 10.1, as indeed we were expecting it to be. Now the next aspect to this is the equation to use for the exponent in the Richardson and Zarki's equation. So we have the calculation, which I'll go through in a second or two, and the n value comes out to be 3.49. So let's actually go through that. So we know that the value here is 10.1, and if we put 10.1, the particle Reynolds number, into this equation just here, because we're at a particle Reynolds number between 1 and 500, then that gives us the exponent, the n value, to put into Richardson and Zarki's equation, which is just there. So this obviously is the Richardson and Zarki equation that we're using. So it was 10.1 was the particle Reynolds number. 3.49, as we saw on the spreadsheet just a few moments ago, is what the value of n is from this equation, and then the superficial velocity is the voidage, which we calculated in part 1, times by the terminal settling velocity, which we're being given, 0.783, and that calculates the superficial velocity for the process, and that comes out to be a value of 0.55 meters per second. 0.55 meters per second. Okay, so that's answer C just there, is the superficial velocity. Great, that's not the end of the story, because we've been asked to do one additional calculation. So the superficial velocity is down here, and this is the velocity required in order to fluidize the bed at that voidage of just over 90%. So we decided that is 0.55 meters per second. Okay, now the final bit we're asked for is the gas flow rate, and Q, if we call Q the gas flow rate, then that is equal to the velocity, the superficial velocity, times by the cross-sectional area. Okay, so that is our last calculation that we need to make. So let's just push that up a little bit. So the superficial velocity was 0.55. I'm going to have to use SI units for this. We need the cross-sectional area, which is pi d squared over 4, as it was before. But now the diameter isn't 30, it's 0.3. 0.3 squared all over 4. Okay, so if I go back to my trusty old calculator, cancel what we had there. So we have 0.3 times by 0.3 times by 3.14 times by 0.55, all divided by 4. That gives us a value of getting trouble with my pen again, 0.033 meters cubed per second, which is 0.039. Yeah, which is actually answer C, just here. So that's actually answered all the questions, but there is a little bit I'd like to just add on here. Let's just investigate what we were doing a little bit further, because there's our particle Reynolds number, which we calculated to be 10.1. That was our value of the Richardson and Zaki exponent, 3.49. The U0 of 0.55. We've got everything we need here to calculate the modified Reynolds number. So the modified Reynolds number for a 90% or 0.902 voidage with a superficial velocity of 0.55 and the density of the fluid and the viscosity of the fluid gives us a modified Reynolds number of 12. And if you remember, the modified Reynolds number threshold for significant turbulence is 2. That's the threshold between so-called laminar flow and turbulent flow through our porous media. So what this implies is that we've got actually quite significant turbulent flow inside the porous media. Well, okay, the Richardson and Zaki equation that we have just here isn't a streamlined flow equation. It's really actually just an empirical equation that relates the superficial velocity to the voidage, or 1 minus the solid's concentration. It assumes no laminar flow or turbulent flow. It's just an empirical equation because arguably the value of n can be changed to fit whatever the data says. However, it's less likely to be reliable when we have high degrees of turbulence. This is obviously a gas fluidized bed. The density of the gas is down here, 1.29 kilograms per meter cubed. That's clearly not a liquid, that's a gas. So this is a gas fluidized bed. There's a reasonable degree of turbulence. It's quite likely that there's going to be bubbling taking place. So we've answered the question correctly based on assuming particulate fluidization, but whether there really is particulate fluidization or not, that is fairly debatable. So just to sort of recap, if we increase the fluid, we would be expecting the bed height to increase nice and uniformly to this value of 0.902, that the voidage to 0.902, which is what we were asked to calculate. But there is a possibility that gas bubbles could actually form here and shoot through the bed very quickly, and therefore the real bed expansion might be less than what we've predicted. Why less? Because these bubbles shoot through faster than the surrounding gas. So if you like, it's a short circuit. It's a way of getting the gas into the bed, through the bed, out the bed again, and the displacement of those bubbles won't be noticed for so long because they're moving so fast. So in fact the bed height might actually not be what we've predicted. It could be lower. I guess from a design point of view that probably isn't so bad, because particulate is probably going to give you the greatest bed expansion calculation, and if it does actually bubble, the bed expansion probably is going to be less. So from a design point of view, that's not quite such a bad thing to overestimate the bed height. But we know the result is a little bit suspect because we've treated it in a particulate way by calculating by doing that calculation, whereas it could be bubbling. Okay, in fact the next question deals with bed expansion of a bubbling bed. Okay, bye.